Hi, I hope by now you've watched my introduction video, which is a kind of high-level introduction to ANOVA, or analysis of variance. And in this video, we'll be walking through an example. Most importantly, I'll show you how to plug numbers into all the formulas for the ANOVA. So we'll be working with an example where we have three different groups of individuals: a group of individuals who's not optimistic about the future based on their own self-report, a group of people who is moderately optimistic or somewhat optimistic about the future, and then a third group of people who reports to be very optimistic about the future. And our research question is, do people with different levels of optimism have different levels of locus of control? So locus of control is a trait that determines how much control you feel like you have over your own life and the things that happen to you in your life. So we have some data here. We have group one's locus of control scores. You can see over here. So this is the raw data in the left-hand column. And I move quickly through the rest of this little table because it's something that you've seen many times before now. But over on the left, you see raw locus of control scores for 5 individuals in group 1. Remember, group 1 are the individuals who say they are not optimistic about the future. And we can calculate the mean for group 1 is 16.2. So on average, people who are not optimistic about the future have a locus of control score of 16.2, according to our study. And because we know we're going to need it for our formulas, the next thing we do is we go ahead and calculate deviation scores for each person, square deviation scores for each person, and then sum that column to get our sum of squares for group 1. So sum of squares for group 1 is 26.8. Alrighty, so we can do the same thing for group 2. This should say 2 here. So for group 2, we have 5 individuals as well who have a mean locus of control score of 13. And we calculated deviations and squared deviations for each person and got a sum of squares for group 2 of 18. And finally, we do the same thing for group 3, the people who are very optimistic about the future. People who are very optimistic about the future, there's 5 of them in our study, and they have a mean locus of control score of 10.4. Again, we've calculated deviations, squared deviations, and a sum of squares for group 3 of 57.2. So by now we've captured 6 pieces of important information. We have 3 group means and 3 group sum of square values. And I have those values here in these 3 tables. So group 1 mean, group 2 mean, group 3 mean, the sum of squares. I've also made note of the degrees of freedom for each of the groups. Remember, degrees of freedom is n minus 1. Each group had 5 people, so 5 minus 1 is 4 for each group. So each of my groups has 4 degrees of freedom. And there's one final piece of information here that I'm listing for each group, and that is the estimated population variance. We have one estimate coming from group 1, one estimate coming from group 2, and one estimate coming from group 3. And we calculated those estimates for each group using this familiar formula. The estimate for population variance is equal to sum of squares over degrees of freedom. You've seen that in our t-tests, our independent samples t-tests, and you're also seeing it now for ANOVA. So sum of squares over degrees of freedom for each group will get us a population variance estimate, or S squared, for each group. So you see that we have 3 different guesses for the single true population variance. And you might be asking, why is there only a single true population variance? Remember, it's because we are assuming homogeneity of variance. or that all the populations have equal variance. So I have 3 different guesses for what the correct variance is. What can I do to resolve this? How about I just take an average? So I have 3 different guesses. Let's add those together in this formula and then divide by 3, or the number of guesses, right? Which is denoted by n subgroups. And I get an estimate for my single population variance of 8.5. And 8.5 is just the average of 6.7, 4.5, and 14.3. So I say, I think that the actual population variance for all the populations, 1, 2, and 3, is 8.5. That's what my estimate will be. Great, so we have calculated MS within, or S squared within. Remember that our F statistic is MS between over MS within. So we've calculated MS within, and it's 8.5. Perfect. Now we need to tackle the numerator. Remember, the numerator, MS between, or the variance for between groups, takes a few different steps. It's a little less straightforward than the denominator. And recall from my lecture, I said the very first thing you want to do to tackle that numerator, MS between, is to calculate the grand mean. So right in here, I have the grand mean calculation. We have the mean for group 1, the mean for group 2, and the mean for group 3. The mean of those 3 values is 13.2. So now that we have the grand mean, we know the mean is 13.2, we can calculate the sum of squared deviations using that grand mean. So you can see I have the whole numerator, the sum of squared deviations, spelled out for you here. We have our deviation for group 1 squared plus our deviation for group 2 squared plus our deviation for group 3 squared. So that's the deviation for group 1 is mean minus the grand mean. The deviation for group 2 is their mean minus the grand mean. The deviation score for group 3 is that group's mean minus the grand mean. We need to square each of those deviations and then add them up to get the sum of squared deviations at the group level. And then we divide by degrees of freedom. So sum of squares over degrees of freedom. So sum of squares over degrees of freedom gives us a value of 8.44. Now this is the variance of a distribution of means. So we calculated the variance using sum of squares over degrees of freedom, but it's for a distribution of means because we used group means to get this value. So now we need to work backwards from the variance of the distribution of means to the variance of the populations. So remember, we're going to use this formula here, which I introduced in my previous lecture. So we just calculated this value on the previous slide, and now we need to multiply it by n to get the between groups variance estimate. So S squared sub m was equal to 8.44. We multiply this by 5 to get MS between equal to 42.2. And that is the second piece of information we needed for our test statistics. So we have MS between, again, over MS within. We've calculated both of these. So we're done with step 2 of hypothesis testing. In step 3, let's figure out, before we go ahead and compute our test statistic, what the critical cutoff value for our test is. So we're going to use a two-tailed test. For now, always assume that you're doing a two-tailed test for the ANOVA. The significance level, or alpha level of the test that we will use is p is less than 0.05. And we need to look up 2 different degrees of freedom. There's the degrees of freedom in the numerator, or the between group degrees of freedom. is number of groups minus 1. So we have 3 groups here. So numerator degrees of freedom is 2. So that's right here. Numerator degrees of freedom is 2. Then we need to find the denominator degrees of freedom, or degrees of freedom within. And remember from the previous lecture that this is degrees of freedom for group 1 plus degrees of freedom for group 2 plus degrees of freedom for group 3. So that's 4 plus 4 plus 4 gives us denominator degrees of freedom of 12. So this is now like a little game of battleship. We find our denominator degrees of freedom, numerator degrees of freedom. Within our denominator degrees of freedom, we have to pick our significance level of 0.05, and we find a critical cutoff score of 3.89. Now we can finally calculate our test statistic. And we have calculated both the numerator and denominator on previous slides. So we can do that math to get an F statistic of 4.96. Remember, my critical cutoff value was 3.89. The F distribution is positively skewed. It looks something like this. And so you can imagine our critical cutoff value of 3.89 here, and our F statistic is 4.96. So it falls in this critical region, and we conclude that we reject the null hypothesis. And in other words, the findings suggest that there are significant differences in locus of control across those who are not optimistic, somewhat optimistic, and very optimistic about the future. And then you can see that there's this funky, it looks like a different language here, part of the sentence. That's how we report our ANOVA results in APA format. So F on 2 and 12 degrees of freedom, that's degrees of freedom between and degrees of freedom within, so those are your degrees of freedom values, is equal to 4.96 at the P level of 0.05. And there's a really important caveat here. Remember that the null hypothesis that we are rejecting is that all the means are equal. So if I reject this null hypothesis and say not all the means are equal, it only tells me that at least 2 of these are different. They're not all the same, but some of them could still be the same. So the ANOVA, importantly, only tells us whether all the groups are likely to be the same or all the groups are not likely to be exactly the same. So we would do something called a post hoc analysis at this point. Now that I've rejected my null and I know that not all the groups are the same, I would do a post hoc analysis to determine where the differences lie. So I've rejected my null hypothesis. Not all the means are exactly the same. However, I don't know which ones are different from one another. So at this point, I would do a post hoc analysis to determine which groups are significantly different from one another. Send me an email if you have any questions about this material, and also, again, make sure that you utilize the discussion forum on Canvas where you can discuss with your peers or with me about any confusion that you're having.